Okay, so welcome everyone to this week's Physics Club. It's a pleasure to be introducing Andrea Alu, who's here from the City University of New York. Andrea is one of certainly the world leaders in the world of what I would call complex wave phenomenon, which includes things like invisibility cloaks and super resolution imaging and non-Hermitian physics and the like. Andrea runs an experimental group and a theory group at CUNY. He got his PhD from Roma Tre, was a postdoc at the University of Pennsylvania, and then joined the faculty of UT Austin in 2009. During his stay there, he held multiple endowed chairs on the faculty, and in 2018 moved to CUNY to become the Einstein Professor of Physics, which sets a certain standard, and the founding director of the CUNY Photonics Initiative. Early on in his career, he received Young Investigator Awards from the AFOSR, from DITRA, from the American Chemical Society, from IUPAP, and from NSF. Later on, he received the Optical Society of America's Adolph Lamb Award and the National Science Foundation's Alan T. Waterman Award. He is presently a fellow of the AAAS, the APS, the OSA, the IEEE, the National Academy of Inventors, and the Simons Foundation. So it's a real pleasure to have you here, and I will hand it over to you.
Thanks. Thank you, Jack. Thanks, everyone, for the kind welcome today. It was a great day. As Jack said, I'm going to tell you what we've been doing in the area of manipulating light using structured materials, metamaterials. So as one slide introduction of why we are looking into gaining more control over light and other forms of waves. There are many of our day-to-day technologies that leverage strongly wireless electromagnetic fields, from communications to sensing to imaging to energy. And the plethora of materials we use to build the technologies around these functionalities are quite limited. So metamaterials offer us a way of structuring functionalities into materials through geometry. So the idea is to build nanoscale structures using nanofabrication tools, and the materials, underlying materials, are actually quite simple, common. These images here show silicon on glass or some silver or gold structures on transparent dielectrics. But the idea is that by structuring the geometry, the shape, the alignment between different layers, you can actually engineer emerging properties, optical properties that are very different than the constituent elements. Typically, we rely on resonances and symmetry. Our group mostly relies on rational designs of these structures, so we like to understand what's going on. So as you see, the structures are quite regular in their response, but there are also many exciting developments in using optimization tools to enhance these properties. The field is very active, many groups, including several in the audience, that are leveraging these ideas for multiple functionalities of interest. So my talk is structured in two parts. In the first part, I will talk about using space to manipulate the wavefront of light. And specifically, I'm going to talk about one application I'm excited about, this manipulation of incoherent radiation. And in the second part of my talk, I will also discuss how to use time to manipulate in different ways the wavefront of incident. So using space to manipulate electromagnetic waves and light has a very long tradition. Now the buzzword is metasurfaces. That comes from a couple of seminal papers about 15 years ago that showed how by nanostructuring an aperture it's possible to imprint a functionality of choice. And in these early works, and in fact even today many of the application works in this area, people use a simple input-output transfer function that locally controls the output of the scattered fields through sub-wavelength elements that can locally tailor the amplitude, the phase, the polarization of the scattered fields in transmission, reflection, and scattering. This approach has been very powerful. It actually draws back to the 60s, 50s, in the field of phased arrays, reflect and transmit arrays at radio frequencies. But it turns out that there are fundamental limits as to how much this can work in terms of building extreme manipulation of light for two fundamental reasons. One is that light fields don't like to be confined. So typically, this assumption that each pixel interacts solely with the fields locally exciting the structure is a very poor assumption. And typically, there are a lot of coupling fields that kind of interfere with this simple picture. And second, as this slide tries to explain, there is a achromatic aberration issue that comes from the fact that different frequencies are affected by the same structures in different ways, oftentimes in unwanted ways. If I try, for instance, to build a lens out of this aperture by applying a parabolic phase profile, I can build a very good lens at one frequency, but then this focusing will be smeared at other frequencies because of the natural dispersion of the response of these nanostructures. So the spectral control of these local metasurfaces, as we call them, is quite poor. In the last few years, we and several other groups have been looking at ways of extending this input-output transfer into a more complex operator form, in which the output depends not just on the local excitation at the same point, but actually more on the distributed excitation across the aperture. And interestingly, there are various rational ways of approaching this that allow us to gain control over the spatial as well as the spectral response. In fact, generally we can control space and time, frequency and momentum, and polarization of the response. The way that we have been rationally understanding this type of approaches is to leverage highly resonant, delocalized resonances, typical of low contrast gratings, but then through symmetry arguments introduce perturbations at the right locations that do not affect the long-range interactions across the aperture, but that structure the profile in reflection or transmission. This picture tries to explain that we can build metasurfaces that are essentially transparent out of band, but that in band can carefully shape the response in reflection or transmission in terms of polarization, amplitude and phase profile, avoiding chromatic aberrations and allowing to actually see through the surface for frequencies in which the design is not operating yet. The idea is really to build on the concept of a grating. So by the way, if I contrast it to the local approach, here we, instead of trying to kill this coupling between elements, as in the pixel by pixel approach to design, we are actually championing this long-range coupling that happens naturally in highly periodic structures. When you have a low contrast periodic grating, you typically have a very nice dispersion relation that tells you that for certain frequencies and certain transverse momenta, you can hit a very strong resonance, despite the fact that each of these elements on their own is highly non-resonant. It's almost a perturbation in terms of, has a very weak scattering. In fact, when you try to describe this mathematically, typically you can use quite powerfully the concept of temporal couple mode theory, this type of dynamic equations that tell us how the temporal dynamics of the mode depend on the leakage rates into the available channels and the coupling in and out of the excitation. In these equations, as you see, there is actually no space. Even the name of this technique is called temporal couple mode theory, because space here is boring. Essentially, the only thing you get out of a grating is specular reflections, conserving momenta because of the high periodicity of the structures. What we have shown is that with non-local metasurfaces, you can build the perturbations across these lattice to define grating modes that have a spatial profile of choice. You can add the space into the picture. So I can do the same type of selectivity in frequency and momentum that I get from a grating, but now I can do it for a wavefront, not for a plane wave. I can structure this in space. And an example of this is this metal lens. This is probably the first example of this type of devices. It's a transparent film in which we have a lattice, an underlying periodic lattice that is perturbed with a parabolic phase profile of leakage of the underlying lattice resonance in a way that when you excite it with a plane wave, it selectively resonates at a specific frequency, but instead of simply reflecting, it actually focuses the beam. But out of band, this lens actually is transparent. And in this way, you avoid the chromatic aberrations that would emerge in this type of, in fact, they must emerge because of dispersion for passive films in this type of structures. And you can use neighboring wavelengths for other functional, or even different polarizations for arbitrary wavefront patterning. In fact, in this same paper, we showed a stack of 3 surfaces that do different operations to different wavelengths of choices, or even for the same wavelength to different polarizations. An important application of this type of structures is augmented reality. There is a great need, as you know also from commercial companies, for this type of devices that allow you to add information onto a scene. Today, augmented reality devices capture the background around you, digitize it, and project information on top. This is a very inefficient way of realizing this type of responses because it adds latency and it requires a lot of energy. By having these transparent films that can selectively introduce resonances in which you can actually not only project information but also process it with light, you can realize quite impressive functionalities, adding directly into the background that you see through a lens. And this is going into the next generation of eyewear devices as well as for automotive applications. But what I'm going to tell you today is one specific aspect I'm quite excited about of this technology that is in controlling incoherent oscillations of matter that comes from heat or from photoluminescence. The idea is that having a highly delocalized resonance with a high Q factor can actually provide coherence to otherwise incoherent phenomena like thermal radiation. Light from emerging from hot bodies or photoluminescence are the most ubiquitous forms of radiation that we see every day around us, from the sunlight to the illumination in this room. The problem is that it's difficult to tame this type of light, very different from a laser, because they are highly incoherent both in space and time. Already many years ago, about over 20 years ago, Jean-Jacques Greffet and several people after him showed that if you start from a phononic material with a strong coupling of light with phonon resonances, and you structure its surface with periodic gratings, you can actually outcouple these oscillations selectively to specific frequencies and specific angles, specific plane waves, for the polarization of the polaritons supported by this surface. And this work showed that the structuring can provide coherence to thermal radiation. However, again, the spatial structure of this radiation is very boring. It's determined by the phonon resonance of the material and by the periodic spatial structure. It's only for plane waves with one polarization. Can we do better than that? The goal is to demonstrate, as I will show you in the next slides, that I can build, through structuring, thin films of very common materials, not phononic at all. This is actually silicon on glass with a thin layer of gold underneath to enhance radiation from one side, that in which the structure of this silicon film can pattern the thermal radiation. So by simply heating this structure, we can create polarization of arbitrary, thermal radiation with arbitrary polarization, wavefront shaping, even vectorial holograms of the radiation from this surface. This is not driven by lasers, as all the structures I showed you so far in the previous slides, but is driven by incoherent oscillations of matter in the underlying material, in particular in the amorphous silicon that we use for the patterning. The idea is to build up one of these spatially structured lattice resonances. This is actually the ingredient we use, and then populate it not through thermal, through coherent excitation through a laser, but instead by just heating up the surface. And the goal is to realize radiation at arbitrary polarization, at arbitrary angles, and even define a spatially structured radiation. So these are some of the initial experiments we did now more than a year ago. These are the nanostructures that we built. The colors here indicate two classes of symmetry groups that we used to pattern the structures. And here we wanted to show 6 metasurfaces that emit selectively the polarization of choice. The numbers here are normalized to black body. So this tells you how close you are to black body. It's already surprising that you can get large emission from a poorly emitting material like silicon. The bandwidth is also impressive. This indicates high temporal coherence of the response. And what is impressive is that we can define a circularly polarized or arbitrarily linearly polarized radiation because the other orthogonal polarization doesn't emit. So this shows that you can imprint an arbitrary profile of polarization of electric fields into the far field of these structures by simply heating. If you have that control and that large temporal coherence, then you can define a phase for the response. Then we use concepts of geometric phase to imprint a pattern, spatial pattern of thermal radiation in far field. The idea here is that through proper geometric rotations, in this plot here, these are geometrical parameters that define basically the orientation of these structures with respect to each other in the unit cell of the design. By playing around the high symmetry point of the lattice, we can, and encircling it, we can get out any phase, 0 to 2 pi, maintaining a high degree of circular polarization and, most importantly, a high degree of temporal coherence across the entire aperture. And this allows us to shape our wavefront of choice with an arbitrary phase across, by basically picking these elements as our unit cells across the aperture.
Andrea?
Yes.
Can I ask you a question?
Yeah, of course.
What would, just like very naively, I could also get circularly polarized light from a black body just putting a polarizing filter in the far field.
Absolutely.
This is not that.
Yeah, so in fact, I was discussing this before in my one of the meetings before. We were discussing this. In this paper, the first figure, this is a theoretical paper in which we spelled out the ingredients to achieve this. And indeed, the first figure of this paper, that I'm sorry I don't have in these slides, shows a black body that is emitting incoherently. And then what does it take to transform this emission into this shape, for instance? What would it take? And what it takes is a stack of many optical components. First of all, you need a high Q filter that rejects most of the radiation, broadband Planck's law radiation from the black body. Then you need the polarizer, quarter wave plates, SLM or some form of modulation in unprecedented phase. After all this stack, you reject most of the heat coming from the black body and you get through something like this actually. In doing that, of course, you have various challenges. First of all, this is a large footprint. Second, all of these components are going to get heated and get inefficiencies in this, and you need to keep heating. The material is emitting a lot, but most of the energy is wasted into heating other components that may actually have their own black body radiation that may kill actually what you want to achieve. So there is actually a big challenge in realizing these types of responses. In the physics community, in these last 20 years, since this seminal work of Greffet, there has been a lot of interest. In fact, I didn't go into the details, But there were some interesting arguments, theoretical arguments, in several papers that claimed it would be forbidden to realize some of the functionalities that we showed. For instance, is it possible to realize a surface, structured surface, that emits circular polarized light with certain handedness in one direction, but not emit the opposite handedness in the other direction? We showed not only that this is possible, but actually we did an experiment demonstrating emission at an angle compared to the normal with a high circularly polarized response, but not in the opposite. That, by the way, has an interesting implication that our surface, as it emits, experiences torque, because it's emitting spin, and linear momentum, so back action from the emission. So there are some interesting features here. But you're right, in principle, if I had ideal stack of optical elements, very efficient, and that are purely reflective and that don't get heated, then I could get the same functionality as some of these with a stack of layers. We do this in 100 nanometer thin film of structured silicon without suffering from other emissions that may come. So this is an example of a meta lens, thermal meta lens. Again, it's a structured thin film of silicon that I just heat. And the emission is highly coherent, quality factors in the range of 140, focused emission at one point at a height from the surface of choice. These are experiments and simulations. To achieve this, by the way, it's very important to not only realize the highly coherent high Q resonance, but also to engineer the dispersion of the underlying modes. A key here, we proved this also theoretically in another paper that I can refer you to, is that the dispersion of the mode, rather than being parabolic and normal incidence, must be linear. This gives you a lot more efficient focusing at normal incidence so above the surface for this type of surfaces. So this is a focus for left-handed polarization. So it is polarization resolved. In fact, for the symmetries of this structure, the right-handed polarization experiences the opposite phase dispersion, and it creates a virtual lens. So this is in the negative. You see at minus 50 millimeters from the surface, we get a virtual focus from the lens. And you see that the linear dispersion of the response. You see it here, actually. This actually are measurements on the focal plane for left-handed polarization. What we see is that there is a rainbow of emission that is linear with the position, and that can serve as an efficient form of spectrometry, because you are creating a rainbow of focuses that is displaced along the plane. And this is our thermal hologram attempt. We try to imprint in the surface. This is the most extreme control we could think of in the context of thermal emission. So we wanted to imprint this silhouette of this the Paris State building into the structure, and we wanted to imprint it vectorially. So the two arms is imprinted with the opposite circular dichroism. One is left-handed, one is right-handed. So we have control pixel by pixel in space over the holographic projection at a distance from the surface. And we do see also in experiments these two lines. By the way, the resolution here is limited by the way we capture. It's not easy to do these measurements because there is a trade-off between spectral and spatial resolution in the imaging of this emission, but we do see indeed this evidence of a spatially structured vectorial hologram that is driven by thermal emission. What's exciting is that anything you can think of that we do with periodic gratings, with lattice resonances, we can now do with spatially structured spatial structuring at the level of the individual unit cells. So we can do nonlinearities. This is very recent papers in which we showed enhanced third harmonic generation from a metasurface with a patterned profile in space. We can do polaritonic responses. This is initial evidence of a polaritonic condensation by coupling one of these metasurfaces to organic molecules. Extraordinary optical transmission, I was discussing this with Owen today. Basically, the idea that is probably over 20 years old, that if you have an opaque screen with small apertures and you can transmit more than what the geometric ray optics picture would allow you to do, it has been demonstrated for plane waves, and now we can actually imprint a structure on the extraordinary optical transmission beam that comes out of this device. And light-based computing is another, could give a full talk on this. We've been working quite extensively on using these tools not only to spatially structure but to the wavefront, but also to engineer the dispersion in frequency and momentum to realize forms of Fourier optics responses based on a single structure surface. But in the interest of time, I want to move to the second part of my talk. Yes, exactly. Moving to the time part and tell you some of the exciting things we've been thinking of in the area of using time instead of space to structure wavefronts. So what I showed you so far can be simply sketched into this simple diagram in which this axis here is space, this axis is time, the red arrow is a wave that travels in 1D in space, and at some point it meets a static boundary interface in space. We all know from electromagnetics 101 that at this interface the wave experiences refraction, in which the phase velocity changes, and reflection, in which the phase velocity is reversed. If I have two of such interfaces, I build up resonances that come from multiple interference between reflected fields. This is how we build all the what the nanostructures we build do. They are building nanoscale resonances that shape the fields. These structures are very good at controlling momentum for the simple reason that we break rationally the spatial translational invariance of wave propagation. So by breaking the spatial symmetry, we control momentum, but typically frequency and energy here are conserved. Of course, if we work on non-Hermitian systems, as Jack beautifully does, and many of us, the energy is not conserved, but because the systems are not conservative. But typically, this type of spatial boundaries are not very good at controlling exchanges of frequencies and energy, unless you go into nonlinear systems. A good picture for schematically described spatial scattering is a mirror that realizes the image of your face or the echoes in the case of sound. Temporal scattering is the dual phenomenon. They uses time instead of space to realize reflections and transmissions. In this case, in this 1D picture, my wave hits a temporal boundary when the medium that contains the wave abruptly changes its optical properties uniformly in space. When this happens, because of the duality of Maxwell's equations, you can get temporal refraction and temporal reflection. Duality is broken only in the way where reflection is. In spatial scattering, reflection is in medium 1. In temporal scattering, because we cannot go back in the past, it is still in the future, but it is a broadband instantaneous form of time reflection. In this phenomenon, time reversal. In this phenomenon, the frequency is agnostic, similar to here. Also here, you can have multiple interference of reflected and transmitted waves in time that allow you to create resonances. Resonances here are not necessarily selective in frequency, like here, but they're selective in momentum. It's the dual. In fact, in these systems, the momentum is conserved because spatial symmetry is preserved, but frequency and energy are very easily controlled in an abrupt and instantaneous way. This is the picture that corresponds to this, the dual of this, indicating that you have time reflections. You can time reverse the image, so you see the back of your signals, not the front, and you efficiently change the frequencies without distorting the overall signal. You can do actually surprisingly interesting things in this regime, with the caveat that you have only one dimension, that is time, instead of three.
So everything was red was blue shifted there.
That's right, yeah. And you can decide if it blue shifts or red shifts depending on how you switch. If you increase the index or reduce the index.
Andrea, you said that things will not end up getting reflected backwards in time.
That's right.
But you do have these arrows there. Do those dashed arrows not happen? Or?
Yeah, the dashed arrows don't happen. These are forbidden by causality, unfortunately. But yes, we only get the solid ones.
I don't know if the universe would work.
Yeah.
Maybe it's good.
Yes, exactly.
Good, you can publish that.
So by the way, there have been this idea of temporal reflections is dated. The first paper that we are aware of is from Morgenthaler, 1956, I believe. But they've been demonstrated around 2006 for water waves by the group of Matthias Fink. And we demonstrated a couple of years ago for the first time the electromagnetic form for electromagnetic waves. Clearly, it is a challenge to do this for electromagnetic waves for the simple reason that the waves go very fast, and you need to be faster than the wave to observe this effect. It has to be an abrupt change, has to be uniform in space, and has to be large enough to create a form of mirror. Right? In the same way as to have a good spatial mirror, you want to have an abrupt spatial interface and a large contrast in impedance. Here is the same problem. Materials don't like to switch fast and by a lot, so it's difficult to find electromagnetic or optical materials that do this type of phenomena. The trick we found is to use a strip line. So these first experiments were done at microwave frequencies in a microstrip that is loaded by a dense array of switches. Switches can be triggered very fast, but they do not change, they do not have a reactive response to help us change the impedance of the material. But we can connect them to static capacitances that actually give you a large reactance. So the idea is to load and unload this strip line very fast to change abruptly and by a lot the effective permittivity of the material. This is how the experiment looks like. It's a 6-meter long meandered strip line. We feed the signal here, and while the signal is in this mesh, we trigger all the switches at the same time, and we can realize a time interface. The way it works, I already mentioned briefly. The strip line itself has its own effective inductance per unit length and shunt capacitance per unit length. We basically are adding to this shunt inductance an extra shunt capacitance, an extra capacitance per unit length in this static. So for dense array of large capacitors, you can change this by a lot. And indeed, what you see, this is the dispersion diagram. So it's momentum of the wave and frequency of the wave. A spatial reflection implies conservation of frequency, so the transitions when you meet the spatial boundary are horizontal in this diagram. And these are measurements of the unloaded and the loaded transmission line. So here you see the change in effective index, in phase velocity. Our transitions are vertical because they conserve momentum, but they do not conserve frequency. And to observe time reflections, you need to couple to this negative frequency. You can do it very broadband. As you see, there is no distortion. So you can do it for a very short pulse in time and get actually time reflections. This is indeed what we did. This is the shape of the pulse. There is no carrier here. So it's a really broadband pulse from DC to about, I think this was about 80 megahertz. Later, we have actually experiments that go up to 3 gigahertz now, continuous wave. And then what we measure at the input part, this is versus time after we switch, is the time reflected version of the signal, in which you see that the signal is reversed in time. We see first the end and then the start. And the signal is stretched in time because all the frequencies have been halved here. So this is redshift. In fact, this is the Fourier transform. You see that it's actually non-distorted, abrupt frequency conversion of all the frequencies in the signal. We also see a space reflection that comes from the fact that after you switch, the output part is actually mismatched. So there is actually a back reflection after some time. This is the time it takes to run 6 meters back and forth. This is the time refracted wave, the time transmitted. It's the same as the input, but it's time stretched for the same reason. But it has the same shape. These are actually the retrieved reflection coefficient in time. It's about 15%. We're working on an optical implementation of this. For now, we're working at mid-infrared at about 38, 40 terahertz. And we use highly doped indium arsenide. We excite with a pulse of about 15 femtoseconds. And we can observe also here a large modulation of the carriers that has a sub-cycle modulation of the result. This is the delta. These are measurements in a pump probe system. The change in reflections, it's quite abrupt with the incoming pulse. In fact, if we do the math, this is the change in carrier frequency. We have a sub-cycle modulation with about 4%. So we have the ingredients to observe time reflections. We did not observe it yet, but we're optimistic. We're using a few tricks to be confident we're seeing some time reflection. It's a complicated experiment also because of the frequency we are using, but we have for sure evidence of a sub-cycle time interface and in infrared frequencies. So these effects using actually polaritonic materials, we're also working on some phonon materials. There are a few ways of using materials with strong nonlinearities that have fast responses that should be able to reach the level of responses we need. But I want to tell you a bit about what we are doing on the front of theory and experiments in this context. I was mentioning already a couple of times the relation between broken symmetries and conservation laws. And fundamentally, these are linked to Noether's theorem that tells us that in a conservative system, every continuous symmetry has a conservation law attached to it. For the case of spatial interfaces, this boils down to time invariance and energy conservation. So we know that the transmitted fields plus the reflected fields equal 1. Energy is conserved. The system is Hermitian. For our case, because a spatial symmetry is conserved, we expect that this relation holds. So this relation tells us that the more transmission I have in time, the more reflection I expect. Or if I want a large reflection, I also need to create more transmission. Remember that here we don't conserve energy. We can take energy from the modulation network, but we need to comply with the fact that because we don't break spatial symmetry, if I had a wave that travels from left to right, net, I need to preserve that contrast. So if I want to reflect, I need to transmit more. Now, I will show you in a moment that this is not necessarily true. In fact, I will show you an experiment in which we break this equality. I will explain why it works. These are very fresh results. Basically, what we are trying to do now, if you think of a mechanical analog, I have a ball that is traveling from left to right, and I want to send it back without impacting the translational spatial symmetry. Can I reflect this ball or this wave, reverse it without breaking translational spatial symmetry? I will show you it's possible, but it's get a bit intricate. This is actually connected to famous controversy between what is momentum in materials. Is it Abram or Minkowski momentum? Maybe familiar with this controversy. For vacuum fields, there is no controversy. Everyone agrees. This comes straight from Maxwell's equations. If you have a certain microscopic force, and you can calculate the stress energy tensor, there is this relation that relates the two, and this guided the conservation law is the change in time of the electromagnetic momentum that is E cross B microscopically. In materials, this gets a little bit more tricky. In fact, Abram and also Einstein speculated that the electromagnetic momentum is the E cross H divided by 1 over c square. Probably, Doug, you know all about this. Minkowski instead speculated that it's D cross B. And Griffiths actually addresses this, in my opinion, beautifully. It says that in the presence of matter, what actually matters is only the total stress energy tensor, because you cannot really tell what part of the momentum is in the material and what part of the momentum is in the wave at any instant in time. For monochromatic fields, by the way, when you average this over a period, the differences wash out, because over a period the exchanges between momentum in the material and in the wave exchange periodically. But for time interfaces, this becomes very important, because it's one example in which time domain is really crucial. The moment in which you switch is very important, and because you have to involve a material, because at some point you have to switch from vacuum to something else to enable time interfaces. So we feel that this is actually a nice playground for testing Abraham-Minkowski controversies, as well as to demonstrate that you can actually break this assumption of conservation of momentum, because what matters is what momentum we are conserving. By the way, this is, yeah.
So you break it by hiding it in the material?
That's right, that's right. So basically what we're going to do in very short is to build a material that has strong light-matter interactions, and choosing the right time in which you switch, you trigger at the moment in which there is a lot of momentum in the material, and then the electromagnetic momentum can be reversed by dumping the forward momentum into a material. So you actually see the wave just going backward. There is no forward wave. So that's, in short, is what Doug already mentioned. So yes, temporal scattering is conserves total momentum, canonical momentum, but does not necessarily comply with this law. That actually, if you see any paper from 1956 to today, has always assumed that this must comply. Can we achieve full-time reversal without breaking translation symmetry? I think I'm running a bit out of time, but in very short, short caveat, what did we do? We used the same trick of the strip line that I did before to switch between a dielectric to another dielectric, but now instead I do it with a plasma. How do I do a plasma in a transmission line? Instead of loading it with a bunch of capacitors, I load it with a bunch of inductors. Inductors in shunt correspond to a plasma frequency. So now my transmission line, when it's connected to shunt inductors, actually has a Drude dispersion with a cutoff. And this is actually our experiment. This is how the transition works. When we connect the inductors, we go to free space to a plasma with a plasma frequency that is controlled by this LC that comes from the shunt capacitor of my line and the shunt inductors that I load into it. I can control where this is. And what we like of this system is that it's a 1D problem in which you go from free space to a plasma, and then you switch off, you go back to the free space. So here you can actually write things in a very clean way. There is a lot of, if you are familiar with Abraham-Minkowski debate, there is a lot of issues with how you define momentum. Actually, this you can do it very cleanly. You can write a Lagrangian in a 1D problem. There are no boundaries. Nothing is difficult. You can define at every instant in time what is the electromagnetic momentum, what is the canonical momentum, and what is the material momentum. These are all consistent with the equations of motion in a plasma, and energy densities, momentum densities. The trick here is that as a function of how you implement your switch, your transition, your time interface from free space to plasma and from plasma to free space, you may have different boundary conditions that control where the momentum is going. In fact, the conventional boundary, we call these conventional boundary conditions because the literature has used that over and over in theory papers, assume that when you switch to a material to a plasma or to a, in general, you add carriers, you add these carriers at rest. When you do that, interestingly, the electromagnetic momentum is not conserved and the energy is. In fact, you couple to DC fields that take into account this difference. If you inject carriers that are already in motion with the right speed, given the wave in it, you can actually conserve the momentum of the system, but you do not conserve the energy because you are injecting carriers with kinetic speed. In this case, you actually, if you do it right, you choose the right velocity, you don't induce any DC field. But you can play with this trick. In fact, interestingly, in our transmission line plasma, when you switch on the inductors, you conserve electromagnetic momentum. When you switch off, you dump into the material. And now we have a trick to basically annihilate some of the momentum. This depends, again, on the type of boundary conditions we use in the application of these time interfaces. Let me show you just the experiment. This is how it looks like. We can control the on and off of these inductors switched into the material, and what we find is that as we change the time in which we apply the off, so we first turn it on, we turn the plasma on, then we switch it off, and this phase here indicates the moment we do it in one period. This shows you that depending on when you do it, you can control how much energy is coupled into the reflected wave, time reflected wave, the time reverse, versus the one in the time transmitted. In this upper portion, I have a lot of time reflection. In the lower portion, I have a lot of time transmission. The total momentum in the system, of course, is conserved because we are not breaking spatial invariance. Noether's theorem is obeyed, obviously, in a closed system. But remember the first words that I bolded in the first slide. It has to be a conservative system. So you need to account also for the momentum you dump into the material, in this case in the inductors. If I look at just the wave, then I see large time reflections. And these are actually experiments showing that we do get experimentally a time reflected, time reversed wave without time transmission. By the way, this has implications in particular for cavities. This is the experiment I was discussing at the beginning of Matthias Fink. It's a famous experiment because they did a beautiful video of this, in which they started with this image. These waves are diffracting, then they do a kick to the surface of water, and the image comes back. This is beautiful because it's 2D, but in this experiment, they need to comply with momentum conservation. So what you don't necessarily see is that there is a large time transmitted wave that has to comply with total momentum conservation. So whatever is coming back, there is something bigger than comes out. If I now put a cavity around it, I'm going to have a problem because that wave bounces off the boundary of the cavity and creates a problem. In our full time reversal, actually the wave does not create. The forward wave is dumped in the material. There is no forward wave. And when I put it in a chaotic cavity, I do get actually full time reversal. Because the forward wave, it's actually hidden in the material. I can get back the image in a chaotic cavity. If I do the Matthias Fink case here in a chaotic cavity, I actually get just amplification, a lot of mess. I see there is a little bit, actually you see the image, but there is a lot more going on because of the forward wave. So we claim that this is a form of reversal of entropy, of course only electromagnetic entropy in the cavity, by dumping, hiding what you don't want, the forward evolving entropy of the mode in another form of energy. Anyways, in the last 10 minutes, if I have 5 minutes? Yeah. Okay. I want to quickly show what we can do if we combine space and time. And we have been working for a few years, I know several of you have worked in this area, of trying to mimic rotations, mechanical rotations, through space-time modulation. We've been using this in particular in the context of breaking reciprocity because slowly varying materials combined with the resonance can largely break the symmetry in wave propagation in materials. So a way to mimic rotation is to impart a modulation scheme that rotates with this law. We call this angular momentum bias. It's a way to bias the system with a synthetic form of rotation. And the simplest form of this is to take 3 resonators and modulate the resonance frequency with a phase. by using the handedness of this phase properly, you can realize this effect in the same way, with actually large efficiency. Now, in a perturbative scheme, this breaks reciprocity efficiently, but in a more, I guess, grandiose way, you can tackle a problem well known in the context of astrophysics, that is the idea of extracting energy from a black hole, rotating black hole. This is an idea that draws back to Penrose, and it's called also Penrose superradiance, and it has been also inspiring the work of Stephen Hawking on evaporation of black holes, or and the dynamic Casimir effect. So the idea is that if I have a massive particle that is falling into a rotating black hole, there is a region called ergosphere in which the energy orbits are negative, and if you dump a mass at that when you are in that region in the black hole, you actually acquire mass because you are in a negative energy orbit region, and you get expelled with a larger mass than you dumped. Can we achieve this with rotations? This has been done actually. It was originally proposed by Zeldovich by spinning an object sufficiently fast, and the negative rotational Doppler shift can actually extract energy from this rotation. But of course, this was realized experimentally again for water waves and for acoustic waves. These are platforms in which waves go slower than light, obviously, and so you gain more access to this. But in our system, we can go as fast as we want. Right? This phase velocity with which we rotate can be much faster than the velocity of light. So then we can access regimes in which these negative rotational Doppler shifts can be very large, and we see the analog of Penrose superradiance in a circuit in which we spin synthetically by applying modulation signals. Let me show you just the results. Maybe this is the picture that shows two main effects. One is the reversal of the angular momentum of a wave. If you send in a wave with a certain spin, if you couple to this Penrose superradiance regime, you experience amplification of the time-reversed version of the same of the signal, and that's related to this coupling to negative frequencies that we do when we do time reflection. So it's a form of time reflection, but it happens in the angular momentum scenario. Let me show you just the results. These are for the fundamental frequency. It's this line here. There is nothing interesting here, just the resonance of the circuit. But for the first order Doppler shifted regime, basically the difference frequency, we get that the input angular momentum gets downshifted, but when you hit 0, it emerges on the other side with amplification and with the opposite angular momentum. You have time reversal and amplification. In fact, interestingly, consistent with the Penrose-Zeldovich description, this amplification is proportional to the amount of loss in the system. The more loss you have at any given frequency, the more amplification you observe, because it's a time reversal process broadband across the entire negative frequency regime of the absorption. And we see it here by plotting versus the inverse quality factor. We see an increase in amplification at any fixed frequency. The last thing I want to tell you is that this connects to an original idea from Zeldovich that told us that if this works, then you may expect in a quantum analysis that spinning objects should emit angular momentum radiation spontaneously. And this is indeed what we see. This is also related to the dynamical Casimir effect. Let me show you just the results. Indeed, we see that as we spin harder this circuit, now without exciting incoherently, just using the natural noise in the resistors in the circuit, we see actually highly coherent emission that depends on the amplitude of the modulation. We see actually a form of lasing threshold, nonlinear increase in the coherence and in the amplitude of emission as a function of modulation strength. We also see other predicted phenomena that for this system. In fact, we can measure, of course, increasing line width, increasing selectivity in angular momentum, a form of classical analog of quantum friction. We can observe more energy extracted from the modulation network as we pump stronger because we are emitting more, and even two-mode squeezing. We can actually correlate the quadrature of the voltages at the two signals, and we do see the squeezing effect that comes from this scenario. I stop here in the interest of time. I just want to say one last slide that this type of ideas of using space and time for manipulating waves in extreme ways connect nano-optics, radio waves, heat, but also sound, static mechanics, and even optomechanics, classical and quantum effects. It's a powerful paradigm, especially if you think from the theory perspective. All of this come together, and the structuring in space and time offer exciting opportunities for extreme wave manipulation. I want to thank my group and the sponsors, and all of you for listening. Thank you.
Okay, questions for Andrea? Logan? We'll be recording, so it's helpful if you...
So you have the squeezing at the end. Just to be clear, is that classical squeezing?
Yeah.
All right.
So we have basically one resonance that we pump the tune, and then we see the statistics, because this is driven by noise.
Yeah.
We see the statistics of the quadrature, and we see similar squeezing as you would expect in a...
What I mean is, like, if you were to measure the Heisenberg uncertainty product, like, is it actually like smaller than you could get for the shot noise limited like coherent state?
It's limited by shot noise, basically. So I think it's this 3 dB, right?
Okay.
The limit. It's a classical phenomenon, but we see the same dynamics. We didn't. I mean, we cannot go past it's driven by its room temperature. There is nothing.
It's not a single photon.
That's right.
It's a big signal.
It's a big signal. Yeah.
All right, that's clear. Thanks.
Other questions? I actually had a quick question. So you talked about a wave moving through a medium, and if you can suddenly make the whole medium change its index of refraction, you get these amazing effects. But you said that the time scale on which it has to change, is that really, it has to be one oscillation of the wave?
Less than one.
Less than one, okay.
It's the same principle as when you design a mirror.
Yeah, but if I, really? Like my bathroom mirror, it's...
If your bathroom mirror has adiabatic profile larger than one wavelength, already you suffer a lot from problems. The reflection cannot be as sharp. Actually, we have a paper that we call it tapered time interfaces, in which we solved analytically this problem as a function of, we used some error function to model this transition. And there is a hard cutoff at about 2/3 of a wavelength. You start seeing, so if you wait, so in this case periods, right? Mm-hmm. So if it's over a period, you lose a lot of the time reflection effect.
Okay.
If you want time reflection, you really need to be subcycle.
Okay. Okay, I think we'll take one last question here from Owen.
So in the thermal radiation structures, if you emit into just one mode, then the radiation is temporally and spatially coherent, right? As you start radiating to more modes with different weights, is there a simple way to understand what is the partial coherence of those systems?
Connected. Yeah. I mean, this will depend. That's a good question. It will depend on the underlying structure, and probably you may be able to control actually the coherence between them through, I guess, the resonances. In some ways, it's consistent with this last thing I showed about squeezing, right? That at some point, depending on the structure, I don't know how much control you have over the relation between the two modes, but certainly you will find some relation because it's driven by the resonances.
Yeah, makes sense.
Okay, with that, let's thank Andrea one more time.
Thank you.